National Electrical Code or NEC Section 645.4 paragraph D specifies that the maximum voltage variation permitted is a drop not to exceed 5% from the voltage at the source to any point on the system under normal operating conditions. National Electrical Code Section 215.10 paragraph A number 2 states that voltage drop on branch circuits shall not exceed 3% under normal operating conditions. Therefore, a supply voltage of 119 volts alternating current or VAC for a machine requiring 115 volts alternating current would be acceptable according to National Electrical Code Section 645.4 paragraph D, as it is within the 5% allowable voltage drop. National Electrical Code Section 250.56 paragraph A states that the resistance of the grounding electrode system shall not exceed 25 ohms. National Electrical Code Section 250.56 paragraph B says that where the grounding electrode system resistance at each building or structure is less than 5 ohms, artificial grounding may be used to supplement the grounding electrode system. Therefore, with proper grounding, the resistance should be as close to 0 ohms as possible, but the code does not specify an exact acceptable range. However, it is generally recommended to keep the grounding resistance below 10 ohms. Voltage tolerances are crucial for ensuring the safe and efficient operation of electrical equipment. The National Electrical Code or NEC provides guidelines to maintain voltage levels within acceptable ranges, preventing damage to equipment and ensuring proper functionality. Firstly, understanding voltage drop is essential. Voltage drop refers to the decrease in voltage along a conductor due to impedance. The NEC sets limits on voltage drop to ensure that equipment receives adequate voltage. NEC Section 210.19, FBN number 4 recommends that the voltage drop on branch circuits should not exceed 3% at the farthest outlet for power, heating, and lighting loads, or combinations thereof. Furthermore, the maximum voltage drop on feeder conductors should not exceed 5%. This combined voltage drop ensures that equipment operates within its designed voltage range. Secondly, voltage tolerance for specific equipment is a key consideration. Equipment is designed to operate within a certain voltage range typically specified by the manufacturer. Exceeding these voltage limits can lead to equipment malfunction, damage, or even fire hazards. For example, motors are particularly sensitive to voltage variations. Overvoltage can cause overheating and insulation breakdown, while undervoltage can reduce torque and cause the motor to stall. Thirdly, voltage regulation is an important aspect of maintaining voltage tolerances. Voltage regulation refers to the ability of a power source to maintain a stable output voltage under varying load conditions. Poor voltage regulation can lead to voltage fluctuations that exceed the acceptable range for sensitive equipment. To improve voltage regulation, consider using voltage regulators or automatic voltage stabilizers. These devices can compensate for voltage fluctuations and maintain a stable output voltage. Fourthly, monitoring voltage levels is crucial for identifying and addressing voltage tolerance issues. Regular voltage measurements can help detect voltage drops, voltage fluctuations, and other voltage abnormalities. Use a multimeter or a power quality analyzer to measure voltage levels at various points in the electrical system. Record these measurements and compare them to the equipment's voltage requirements to identify potential problems. Fifthly, addressing overvoltage and undervoltage conditions promptly is vital. Overvoltage can be caused by utility voltage fluctuations, lightning strikes, or improper wiring. Undervoltage can be caused by overloaded circuits, long conductor runs, or utility voltage sags. If overvoltage is detected, consider using surge protection devices to protect equipment from voltage spikes. If undervoltage is detected, investigate the cause and take corrective action, such as upgrading the wiring, reducing the load on the circuit, or contacting the utility company. Sixthly, grounding is a critical safety measure that provides a path for fault current to return to the source, tripping a circuit breaker or fuse and preventing electrical shock. NEC sets requirements for grounding to ensure that electrical systems are properly grounded. NEC Section 250.4 provides general requirements for grounding and bonding. It states that electrical systems must be grounded in a manner that creates a low impedance path for fault current. This path must be continuous and permanent, and it must be capable of safely carrying the maximum fault current that could occur. Seventhly, grounding electrode system requirements are detailed in the NEC. The grounding electrode system consists of one or more grounding electrodes that are connected to the grounding conductor. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. NEC Section 250.52 specifies the requirements for grounding electrodes. It requires that grounding electrodes be installed in contact with the earth and that they have a resistance to ground of 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode must be installed. Eighthly, bonding ensures electrical continuity and provides a low impedance path for fault current. Bonding connects all metal parts of the electrical system together, including enclosures, raceways, and equipment grounding conductors. NEC Section 250.92 specifies the requirements for bonding. It requires that bonding jumpers be used to connect metal parts together and that these jumpers be sized according to the requirements of NEC Section 250.102. Ninthly, equipment grounding conductors or EGC provide a path for fault current to return to the source from equipment enclosures. EGC are typically wires or raceways that are run along with the circuit conductors. NEC Section 250.118 specifies the types of conductors that are permitted to be used as EGC. It requires that EGC be sized according to the requirements of NEC Section 250.122 and that they be properly connected to equipment enclosures. Tenthly, grounding resistance measurement is essential for verifying the effectiveness of the grounding system. Grounding resistance should be measured using a ground resistance tester. The measured resistance should be compared to the requirements of NEC Section 250.56. If the resistance is greater than 25 ohms, corrective action must be taken to reduce the resistance. Furthermore, regular inspection and maintenance of the grounding system are essential for ensuring its continued effectiveness. Inspect grounding connections for corrosion and looseness and repair any damage to the grounding electrodes or conductors. By following these guidelines and recommendations, electrical engineers and technicians can ensure that electrical systems are properly grounded and that voltage levels are maintained within acceptable tolerances, promoting safety and preventing equipment damage. The National Electrical Code also specifies requirements for grounding electrode systems. Section 250.50 covers the general requirements for grounding electrode systems, stating that they must be designed and installed to provide a low impedance path to ground. This low impedance path ensures that fault current can quickly and safely return to the source, tripping a circuit breaker or fuse and preventing electrical shock. Section 250.52 details the acceptable types of grounding electrodes. These include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and ground rods and pipe electrodes. Each type of electrode has specific installation requirements to ensure its effectiveness. For example, ground rods must be at least 8 feet long and driven into the earth to a depth of at least 8 feet. Section 250.53 outlines the requirements for the installation of grounding electrodes. It specifies the spacing between electrodes, the depth at which they must be buried, and the methods for connecting them to the grounding conductor. Proper installation is crucial for ensuring that the grounding electrode system provides a reliable path to ground. Section 250.56 addresses the resistance of grounding electrodes. It states that the resistance to ground of a single grounding electrode must not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional grounding electrode must be installed in parallel with the first electrode. This requirement ensures that the grounding system has a low enough impedance to effectively clear ground faults. Section 250.64 covers the grounding electrode conductor, which is the conductor that connects the grounding electrode to the electrical system. It specifies the size and type of conductor that must be used and the methods for connecting it to the grounding electrode and the electrical system. The grounding electrode conductor must be sized according to the requirements of NEC Table 250.66. In addition to these general requirements, the NEC also includes specific requirements for grounding different types of equipment and systems. Section 250.110 covers the grounding of equipment, stating that all non-current carrying metal parts of equipment must be grounded. This includes enclosures, raceways, and other metal parts that could become energized in the event of a fault. Section 250.118 specifies the types of equipment grounding conductors that are permitted to be used. These include wire-type equipment grounding conductors, metal raceways, and cable trays. Section 250.130 addresses the grounding of separately derived systems such as generators and transformers. It requires that these systems be grounded in accordance with the requirements of NEC Section 250.30. Proper grounding of separately derived systems is essential for ensuring that they operate safely and reliably. Furthermore, the NEC also addresses the grounding of specific types of equipment such as swimming pools, agricultural buildings, and healthcare facilities. These occupancies have unique grounding requirements to address the specific hazards associated with them. Regular inspection and testing of grounding systems are essential for ensuring their continued effectiveness. Grounding systems should be inspected for corrosion, damage, and loose connections. The resistance of the grounding electrode system should be tested periodically to ensure that it meets the requirements of NEC Section 250.56. If any problems are found, they should be corrected promptly. By following the requirements of the National Electrical Code and implementing a comprehensive grounding program, electrical engineers and technicians can ensure that electrical systems are properly grounded, protecting people and property from the hazards of electrical shock and fire. Let's delve deeper into the practical aspects of voltage and grounding tolerances, emphasizing real-world scenarios and best practices. Firstly, consider a scenario where a manufacturing plant is experiencing unexplained equipment malfunctions. The equipment, designed to operate at 480 volts alternating current, is frequently shutting down or exhibiting erratic behavior. Upon investigation, it's discovered that the supply voltage fluctuates between 460 volts alternating current and 495 volts alternating current due to varying load demands within the plant. This voltage variation exceeds the acceptable tolerance range for the equipment, leading to the malfunctions. The solution involves installing a voltage regulator to stabilize the supply voltage within the specified limits. This ensures consistent and reliable operation of the equipment, preventing further disruptions. Secondly, imagine a commercial building where lighting fixtures are frequently burning out prematurely. The building's electrical system is designed for 277 volts alternating current lighting. However, measurements revealed that the voltage occasionally spikes to 290 volts alternating current during off-peak hours. This overvoltage condition is damaging the lighting fixtures, shortening their lifespan. To address this issue, surge protection devices are installed to the main electrical panel and its individual lighting circuits. These devices protect the lighting fixtures from voltage spikes, extending their lifespan and reducing maintenance costs. Thirdly, let's consider a residential setting where a homeowner is experiencing flickering lights and dimming appliances. The homeowner's electrical system is designed for 120 volts alternating current. However, the voltage drops to 105 volts alternating current during peak hours when multiple appliances are in use. This undervoltage condition is causing the lights to flicker and the appliances to operate inefficiently. The problem is traced to an overloaded circuit and undersized wiring. To resolve this issue, the circuit is upgraded with larger gauge wiring and additional circuits are added to distribute the load more evenly. This ensures that the voltage remains within the acceptable range, providing stable power to the lights and appliances. Fourthly, consider a data center where sensitive electronic equipment requires a stable and reliable power supply. The data center's electrical system is designed with redundant power sources and uninterruptible power supplies or UPS to prevent downtime due to power outages or voltage fluctuations. Regular monitoring of voltage levels and grounding resistance is conducted to ensure that the power quality remains within acceptable limits. Any deviations are promptly addressed to prevent equipment damage or data loss. Fifthly, let's examine a construction site where temporary power is being used to operate tools and equipment. The temporary power system must be properly grounded to ensure the safety of workers and prevent electrical hazards. Ground fault circuit interrupters, or GFCIs, are installed on all temporary power circuits to protect against electrical shock. Regular inspections are conducted to verify the integrity of the grounding system and the proper functioning of the GFCIs. Sixthly, consider a hospital where reliable power is critical for life support equipment and other essential medical devices. The hospital's electrical system is designed with multiple layers of redundancy and backup power sources to ensure continuous operation during power outages or voltage fluctuations. Regular testing and maintenance of the electrical system are conducted to identify and address any potential problems before they can impact patient care. Seventhly, imagine a solar power installation where the output voltage of the solar panels must be carefully managed to ensure compatibility with the grid. Voltage regulators and inverters are used to convert the direct current or DC voltage from the solar panels into alternating current or AC voltage and to regulate the voltage to match the grid voltage. Monitoring systems are used to track the output voltage and power of the solar panels and to detect any voltage anomalies. Eighthly, consider a wind turbine installation where the output voltage of the wind turbine varies depending on the wind speed. Voltage regulators and converters are used to stabilize the voltage and to match it to the grid voltage. Control systems are used to adjust the pitch of the wind turbine blades to optimize power generation and to prevent overvoltage conditions. Ninthly, let's examine a telecommunications facility where a stable and reliable power supply is essential for maintaining network connectivity. The telecommunications facility's electrical system is designed with backup generators and uninterruptible power supplies, or UPS, to ensure continuous operation during power outages or voltage fluctuations. Monitoring systems are used to track voltage levels, grounding resistance, and other power quality parameters. Tenthly, consider a research laboratory where sensitive scientific instruments require a clean and stable power supply. The research laboratory's electrical system is designed with dedicated circuits, isolation transformers, and power conditioners to minimize voltage fluctuations, electrical noise, and other power quality problems. Regular testing and maintenance of the electrical system are conducted to ensure that the instruments operate accurately and reliably. Grounding tolerances are crucial for ensuring electrical safety and preventing equipment damage. The National Electrical Code sets standards for grounding resistance, requiring that it be as low as possible, ideally below 25 ohms. Low grounding resistance ensures that fault currents can quickly and safely return to the source, tripping a circuit breaker or fuse and preventing electrical shock. Factors that can affect grounding resistance include the type of soil, the moisture content of the soil, and the type of grounding electrode used. In areas with high soil resistivity, such as sandy or rocky soil, it may be necessary to use multiple grounding electrodes or to install a ground enhancement material to reduce the grounding resistance. Proper grounding techniques are essential for achieving low grounding resistance. These techniques include using corrosion-resistant grounding electrodes, properly bonding all metal parts of the electrical system together, and ensuring that the grounding conductors are sized appropriately. Regular testing of grounding resistance is essential for verifying the effectiveness of the grounding system. Grounding resistance should be measured using a ground resistance tester. The measured resistance should be compared to the requirements of the NEC. If the resistance is too high, corrective action must be taken to reduce it. Maintaining acceptable voltage and grounding tolerances requires a comprehensive approach that includes proper design, installation, testing, and maintenance. By following the guidelines and recommendations outlined in the NEC and implementing best practices for voltage regulation and grounding, electrical engineers and technicians can ensure the safe and reliable operation of electrical systems. Voltage and grounding tolerances are not merely abstract concepts, but rather essential elements of electrical safety and system performance. Understanding these tolerances and implementing appropriate measures to maintain them is crucial for protecting people and property from the hazards of electricity. Always consult the latest edition of the National Electrical Code and other relevant standards for specific requirements and recommendations.